So yeah, yesterday we talked about these terms, and we talked mainly about two very important terms, the system and the surroundings, all right? And that's what we really need to kind of get encapsulated in our mind. What do we really mean when we're talking about the system, and what do we really mean when we're talking about the surroundings, all right? We also need to keep in mind our terms that were associated with energy, right? So we've got kinetic energy and potential energy. I think that's pretty straightforward, energy of motion versus energy that's stored in some way. And then we've got heat, which is this transfer of thermal energy, okay? And so all these terms become very important. And what I want to do is draw a little diagram to kind of solidify these terms in a little more of a graphic fashion. So if you've got the title calorimetry down, that's great. I'm going to switch to the Smart Notebook, and I'm going to then draw a little picture that I use to represent this stuff. Now, yesterday, we talked about a chemical reaction where I drew a little beaker, and that beaker had some water in it and some hydrochloric acid and some magnesium, and I hopefully got across to you. Well, I'll ask you this question. In my little, well, let me draw it up just to kind of, again, get your mind going straight here. So if I've got a beaker here, and let's say that we've got a lid on it, and let's say that it's made out of lots of styrofoam so that it is what is called isolated, which means no energy is going to be able to leave and come in, and no matter is going to be able to leave and come in. So I've got here some HCl, and I've got here some Mg. It's going to produce some H2, which is going to bubble away, produce some pressure in here, which is just fine, and it's going to make some MgCl2. And of course, that's all dissolved in some water. All right, well, you tell me, what is the system here? What are we studying? What are the things that we want to learn about? What's the system in this picture? Yep. The HCl and the Mg, it's also the MgCl2 and the H2. It's the reactants and the products of the chemical reaction we're studying. So all of our reactants and products here, I'll draw a couple of lines that come from them. All this stuff is what we call the system, all right? Now, it's not what we mean by an isolated system, right? That term isolated describes the container we're using. And I know it uses the word system. That's unfortunate, but it's not the system we're studying. The reactants and products are the system we're studying. Excellent. What's the surroundings in this case? Yep. The water. And the surroundings essentially is the substance or substances, it could be more than one, that are essentially nearby this chemical system that allows it to catch the heat if it's produced, or give heat in if the chemical system needs energy, if it's endothermic. So the water itself is the surroundings. Excellent, all right? And then we've got what I would call the surroundings. The surroundings would be the rest of the furniture that's in the laboratory, and the people and the air, and our styrofoam cup, our isolated system, hopefully keeps the surroundings away from our chemical system so we can study it, all right? So that's the whole purpose of doing it. Now, what are we doing, and why are we doing this type of thing? Why do we need to separate it out? Well, it has everything to do with studying energy transfer. So now, instead of me drawing a picture of a beaker or a styrofoam cup, I want to draw the system and the surroundings as if they're just a container for energy. I don't want to really worry about the actual styrofoam cup and the actual chemicals. I want us to kind of think of it just as an energy reservoir, something where energy is going to be put. So I'm going to clear this screen. Let's just get a new slide here. And so instead of drawing beakers and containers, I'm going to just draw a rectangle, very simple rectangle, right? And I'm going to let that rectangle represent my system. That's the chemical system. And you can think of this rectangle as a bank, all right? Like a building that holds something. Something that's just holding, in a bank it would be money. In this case, it's energy. So let me just make a simple little bar graph to represent the energy that is in that system, all right? And again, this system could be the magnesium and the hydrochloric acid, producing the magnesium chloride and the hydrogen. But I'm just drawing it graphically as something that has a bunch of energy in it. All right, there's energy within that stuff. In actual fact, there's two forms of energy. We'll learn about that today. The two forms of energy, so I'll break this in half. The two forms of energy are EK. There's kinetic energy because the particles are moving, they're wiggling. And there's EP because there's energy stored in the bonds. So now I want you to think of our chemical system not as being physical chemicals, but as being something that holds energy, okay? Like your bank. Your bank holds your money. You may have 2 or more bank accounts. Your total amount of money would be the sum of all of your bank accounts, but you may have a checking account and you may have a savings account. The energy within a chemical system, there's a total amount of energy, and in that system, some of the energy is in the form of kinetic energy. The particles are wiggling, or they're vibrating, or they're moving, and some of it is in the form of potential energy stored in the chemical bonds. Okay? So that's our system. That's what we want to study. That's the thing we can't see. We cannot simply look at some reactants in a cup and say, oh, look, I can see it wiggling. There's some kinetic energy. Let me write that down. That's good. And, oh, look at there. I can see the bonds. I know how strong that bond is. Let's write that down. I can't just, it's like I don't know what's in the bank. It's like having a bank account and having no knowledge about how much energy is in there. Gee, I wonder how much money I have. I have no idea. I can't tell. All right? That's the trick of thermal chemistry, to be able to do some experiments and figure out how much energy is in that thing. How do we do that? We do that by looking at what happens to the surroundings, the water in this case. I'm going to let the surroundings just be another rectangle, except this one's going to be really long, and actually it's so long, actually no, I'm not going to make it infinitely long. Let's just put a box there. All right, this is going to be my surroundings. And that's essentially the water in this case. In most cases in this course, the water is the surroundings. And that water also has some energy, all right? And I'm going to make a pile of energy in there as well. And I'm going to make it a bigger rectangle because the water is a lot bigger than the chemical elements themselves. There's a lot more water around, so there's a lot more. And again, it also has lots of energy, and we're going to put here EK. We're not worried about the potential energy in the water because we're not going to be chemically changing the water. All the water is going to be doing is catching the energy that comes from the system. When the chemical reaction happens, it's going to spit some energy out, it's going to give it to the water, and the water's going to warm up. The water's not going to boil, hopefully, or we'll have to change our experiment. The water's not going to decompose. So we're not chemically affecting the water, we're just affecting its temperature. So it's only the EK we're affecting. So what are we doing? Well, here's essentially what a calorimetry situation does. We take our coffee cup calorimeter with a nice fitting lid, and this is actually crappy because I can't find my good ones, but you get the idea. That look at how isolated that is. There's no way energy can get out of that. Yeah, thank you for giggling, because look at the holes in it. It's all over the place. This is terrible. But this is not too bad right here. So we put in our water and our reactants. We put in the other reactant. The reaction starts. We put a thermometer in. We measure the temperature before. Then we measure the temperature afterwards. And that change in temperature of the water tells us something. And that's what calorimetry is. We put the reactants in. The energy of this system changes, and some of the energy gets transferred to the surroundings. Some of that thermal energy goes to the surroundings. When thermal energy moves, the transfer of thermal energy from one place to another or from one thing to another. We had a definition that defined one of our important terms yesterday. Does anybody remember what that word was? If the thermal energy moves from one place to the next, what do we call that? Yeah, it's called heat. Do you remember the symbol we had for heat? It was a Q. Q. All right? This, right now, is what we want to learn about today. We want to learn that if the surroundings heat up, how much Q did it get added? How much heat did it get? All right? Because eventually, we're going to get to the point where the amount of Q that goes into here is the same amount of energy that came out of the bank, right? Because we have a conservation of energy. If the system loses some energy to the surroundings, then the energy that the surroundings gains must be exactly equal to the energy that the system lost. So by measuring the surroundings, by measuring how the water's temperature changes, we can get an idea on what's happening in the system. Because we can't actually see the system, but we can measure the surroundings. We can measure it by temperature changes. And that's what this is all about. So for today, we're going to learn about the Q. How do we calculate how the surroundings changes, and how do we determine the energy involved? In the next lesson, we'll learn about how that relates to the system, so that we can then make the step of, if some energy leaves, how much energy did the system change by? So today we're learning about the surroundings. We're learning about what happens when a surrounding material gains in temperature, gains in heat, or loses, temperature decreases and loses in heat. All right? Yeah, that's my introduction essentially.